Right, so in today's class, I basically wanted us to finish up on the Hessian determinant. This is something that we started before, so this will be more like revision. So if you remember, when you're given a function and you want to work out whether the critical point is a maximum, a minimum, or a saddle point, we use what we call the Hessian determinant. And how do we get these critical points? With the critical points, you need to work out the first partial derivative with respect to x. We'll equate it to 0. The first partial derivative with respect to y will equate it to 0. Then these two equations, you solve them simultaneously, and that will give you the critical points. Then to test whether this critical is maximum, minimum, or a saddle, we use what we call the Hessian matrix. So you have to come up with the Hessian matrix, which looks like this. So we have fxx, here we have fxy, here we have fyx, and this is fyy. So our second order partial derivatives. And I hope you remember that these two in general are the same. So in general, fxy is equal to fyx. So that is why a lot of times you will see in our Hessian matrix, instead of having fyx, we just have fxy because they are equal. All right. So how does this Hessian matrix actually help us to find or classify our critical points? It's very simple. So we work out our H1. So our H1 here, this is fxx evaluated at the critical points, and then we have our H2, which is the determinant of this Hessian matrix here. And then we have a table to classify our critical point depending on what we have. Okay, so this may be positive, this may be negative, this may be positive, negative, positive, and negative. And here we can say the classification or the nature. Now, whenever your H2 is negative, that is always a saddle point. And here, when it's positive, H2 is positive, you have to look at what your H1 is. If they are both positive, then you have a minimum. And if H2 is positive and H1 is negative, then you have a maximum critical point. For a minimum critical point, we say that this is positive, definite. And this one we say is negative, definite. Okay, so we've done all of this in class. This should not be new. Just going over how it is that we classify our critical points. Okay, so now that we know how to classify our critical points, let's answer this question. Okay, so we said in order to find our critical points, what we need to do is find our first order partial derivatives. So work out fx. And remember, when we are differentiating with respect to x, it means that y is a constant. So the derivative of xy, this is y because y is a constant, and then 1 over x. Keep in mind, or take note that 1 over x, this is x to the power of -1. So when you differentiate, the -1 will come down, and then at the top, you subtract 1, and this is -1 over x squared. So this I'm sure you're already familiar with. So this is 1 minus 1 over x squared, and the derivative of 1 over y is 0 because it has no x, and we're differentiating with respect to x. Then we have the first partial order derivative with respect to y. So when we differentiate this with respect to y, we're left with x. And in the same way, when we differentiate 1 over x with respect to y, this is 0 because it doesn't have a y, so it's a constant. And then this one here, 1 over y, the derivative, done in a similar way will give us 1 over y squared. Okay, now we're trying to show that this is the critical point. It means when we evaluate or equate these to 0, solve them simultaneously, we should get a critical point of 1, 1. So I like questions like this where you are asked to show that something is a critical point, because then you know whether you're right or wrong. Because if you're getting something that is different from this one, there may be more than one, at least one of them should be this critical point. So you always know whether you're doing the right thing or not. Okay, so we know that at the critical points, the first partial derivative with respect to x is equal to the second, to the first partial derivative with respect to y, and this is equal to 0. So we have y minus 1 over x squared is equal to 0. So we'll solve this one. So what we can do is we can multiply everything by x squared. So we'll have x squared y minus 1 is equal to 0. And this means that x squared y is equal to 1. And the same thing over here, we have x minus 1 over y squared is equal to 0, which means that x y squared minus 1 is equal to 0. And this means x y squared is equal to 1. So now we want to solve these two simultaneously. One way to do that is by substitution. So from this equation over here, we can see that y is equal to 1 over x squared. And then we are going to come and substitute it over here so that we solve for x and then we go back and solve for y. So doing that, we have x multiplied by y squared, but y is 1 over x squared, and this must be squared because this is y squared. This is equal to 1. So this is x 1 over x squared is 1 squared, which is 1. And then x squared squared, laws of exponents, means x to the power of 4. This is equal to 1. And you can see that the x there will cancel, and then we're left with x cubed. So we have 1 over x cubed is equal to 1. And that means that x cubed is equal to 1, because if I cross multiply, I have 1 is equal to x cubed. So that means x cubed is equal to 1. And then this means that x is equal to 1 if you take the cube root on both sides. Okay, so now we have our value of x. We come back to the formula for y. We know that y is equal to 1 over x squared. So this is 1 over 1 squared. This is 1. So x is equal to 1, y is equal to 1. Therefore say the critical point is 1, 1. And we have shown that because part of the question said show that it has a critical point at the point 1, 1. All right, now we know what our critical point is. What we next need to do is classify it, determine is this a maximum, is this a minimum, or is this a saddle point. So how do we do this? We need our second order partial derivatives. So okay, so here we have fx. So to get fxx, we just differentiate this again with respect to x. The derivative of y is 0. And then here, minus 1 over x squared. I can rewrite this as minus x to the power of negative 2. And we know how to differentiate this. We have a negative that's already here, and the negative 2 will come down. And then at the top, we subtract 1. So negative and negative will give me positive 2, x to the power of negative 3. And when I rewrite this with a positive exponent, I have 2 over x cubed. And you can see this is positive. So we have 2 over x cubed, which is just 2 over x cubed. And then we can find fxy. That means we take our first partial derivative with respect to x and then differentiate it now with respect to y. So the derivative of y is 1 And then this one over here, its derivative is going to be 0 because it does not have an x. So it does not have a y. So that means it's a constant. So its derivative is 0. So this mixed second order partial derivative is just equal to 1. And then we have y. So we take our first order partial derivative with respect to y, and then differentiate it again with respect to y. So the derivative of x will be 0, and then here the derivative of minus 1 over y squared. When I do it in a manner similar to this one, I will end up with positive 2 over y to the power of 3. Okay, so now I have all the derivatives I need. I write down my Hessian matrix. We know here we should have fxx, fxy, fyx, which we know is exactly the same as xy, because if I were to differentiate this one here with respect to x to get fyx, I would get 1, which is exactly what I have over there. So those two are equal, and then here I should have fy1. Okay, now just substituting my values, fxx is 2 over x cubed, and then fyx, this is 1, and then here I have 1, and the second order partial derivative with respect to y, this is 2 over y cubed. Okay, so I need to work out my h2. You can start with h1 since that one is not too difficult. So h1, this is just fxx, which is 2 over x cubed, and then we substitute our critical point. So remember, our critical point is 1, 1. So x is 1 and y is 1. So we substitute it there. So h1, the point 1, 1. This is 2 over 1 cubed. So this is 2, and this is positive. It's greater than 0. Then our h2, which is the determinant of the Hessian matrix, we know how to find the determinant of a 2 by 2 matrix, the product on the major diagonal. So we have 2 over x cubed, and this is multiplying by 2 over y cubed, and then we subtract 1 by 1, and this gives us 4 over x cubed, y cubed, minus 1. And then, of course, we evaluate the Hessian matrix at our critical point. So we want H2 at the critical point. So our H at the point 1, 1. So this is 4 over 1 cubed multiplied by 1 cubed minus 1. And this gives us 4 minus 1, which is 3. And this is also positive. So our H1 is positive, our H2 is also positive. This is positive definite, and that means the point is a minimum. So we can say that since H1 greater than 0 and H2 is also greater than 0, our critical point is a minimum. Okay, so that is basically how we use the Hessian matrix to find a critical point and then test the nature of that critical point. Okay, now here's another example where we are going to apply the Hessian matrix. So our questions are not always going to be just theoretic like the previous one where it's just some function. Of course, you guys as economists, you want to apply what we're learning here into real life scenarios. So this is a question which I'm sure you're familiar with. You want to see, can we use the Hessian matrix to determine whether we will get a maximum profit? So the question says, Cassie Clothing produces and sells t-shirts and shorts. Each t-shirt is sold for $150 and each short for $180. The cost of producing X t-shirts and Y shorts is given by our formula C. then it can be shown that the optimal profit of Cassie will be obtained by selling 27 t-shirts and 21 shirts. Okay, so here we are being given our critical point. So it means 27 t-shirts, so that means X is equal to 27 and Y is equal to 21. So we are having a critical point at the point when X is 27 and Y is 21. Now it says use the function to determine whether the profit will be maximized by these sales. So we know that this is a critical point. Now we want to find out, is this critical point a maximum or is it a minimum? So what we're trying to maximize is not the cost, but the profit. And you'll notice that the formula for the profit is not given. So what we need to do is work out the formula for the profit. As economists, we know that our profit is equal to the revenue minus the cost. So revenue is our income, how much are we getting in, and the cost function is given to us over there. So if we were to write this out, our revenue, because we get our revenue from selling the t-shirts, we know that one t-shirt costs 150. So our revenue function is going to be 150x plus the revenue from the source. This is 180y. So this is our revenue. And then what we do is we subtract our costs. This is our formula for the cost, and we put it in brackets to show that we are subtracting everything, not just 2x squared. So xy plus 3y squared. Okay, and this gives us the formula for our profit. This is 150x plus 180y minus this negative should multiply everything inside the brackets with minus 2x squared minus 2xy and minus 3y squared. Okay, now we have our critical point, so we're not being asked to work it out or actually show it. What we want to do is just test, will we have a maximum at the point where x is 27 and y is 21? So the procedure, exactly the same one we used in the previous one. We need our Hessian matrix. So our H matrix, you know that this is going to be P, X, X, P, X, Y, Pxy, because Pxy and Pyx are exactly the same, and Pyy. Right, so in order to work out the second order partial derivatives, we obviously need the first order partial derivatives. So we have Px, differentiating this with respect to x, we get 150. The derivative here is 0 because it doesn't have an x. The derivative here is minus 4x. The derivative of this one is minus 2y. And the derivative here is 0 because it doesn't have an x. Then Py, the derivative here is 0 because there's no y. The derivative here is 180. The derivative is 0 because it doesn't have a y. The derivative here is minus 2x. And the derivative here is minus 6y. Okay, so those are first order partial derivatives. We need the second order partial derivatives. So doing that is simple and straightforward. So we have Pxx. The derivative of 150 is 0 because there's no x, it's just a constant. The derivative of minus 4x is minus 4. The derivative of minus 2y is 0. Our next second order partial derivative, we differentiate this with respect to y. This is 0, this is 0, and the derivative here is minus 2. And then y, derivative is 0, derivative is 0, derivative is minus 6. Okay, then we go ahead and substitute it into our matrix. Pxx is -4. And then pxy, this is -2. Pxy again is -2. And then over here we have -6. So we first find our h1. H1, this is pxx. So this is -4. So we don't have to substitute anything because it has no x, it has no y. It doesn't depend on the 27 and the 21 that we got. So our answer is just -1. This is less than 0. Then our H2, we know that this is the determinant of the Hessian matrix. And we know how to work out the determinant of a 2 by 2 matrix. Very simple and straightforward. We have -4 times -6 minus -2 times -2. So this is negative and negative will give us positive. So this is 24 and negative here will give us +4. So we have 24 minus 4 and this is equal to 20, which is positive. Okay, so we have H1 is negative, but H2 is positive. That means what we have here is a maximum. Okay, so you can see that since H2 is positive and H1 is negative, we have a maximum. Okay, so this is confirming that in order to maximize your profits, you need to sell 27 t-shirts and 21 shorts. And it'd be a good exercise for you to try it. Try combinations of t-shirts and shorts and then work out the profit. You will see that the profit you get will be maximum when you have these two values over here. And then the last part of this chapter is what we call the bordered Hessian determinant. So here, what you will have is you have a function which depends on x and y that you want to optimize, but there is a constraint, and this constraint is another function, g. Now, this, I'm sure you can imagine, happens a lot in life because if you want to make a profit from selling t-shirts and shorts, the maximum profit, I guess, is unlimited if you just keep producing these t-shirts, keep producing these shorts and selling them. But in real life, we know that's not how things work. You're always going to have constraints because you need people to make these t-shirts, to make these shorts, and maybe in a week they can only make 50 as your total. So there's always going to be some constraints. So here, what we do or what we have is we have a function that we want to optimize, but it is subject to a constraint. So what we will do to work this out or solve a problem like this is we will come up with a new function. So we say that a new function called the Lagrangian function is formed. And this Lagrangian function is a function of x, y, and lambda. And it is given by f of xy plus lambda multiplied by k minus g of xy. So whenever we're introducing a new topic, it always seems so complicated. But when we work it out using examples, it is very easy to do. So a lot of times you will see that your critical point is given, but when your critical point is not given, what you need to do is work it out the same way we did the other one, and your critical point will be at the point where the first partial derivative with respect to x is equal to the second partial derivative with respect to y, and the partial derivative, the first partial derivative with respect to lambda, all of them must be equal to 0, and then you will solve them simultaneously. So here, this is related to the Hessian matrix, but it is bordered. Bordered in the same way you think of borders in a country or borders in your notebook. You see that there are those lines in your notebook. Those are what we call borders. So here you write H with a bar on top that shows that it is bordered, and this determinant is given as follows. So remember our Hessian matrix. Okay, and then what we do is around here, we are going to border it. And what do we border it with? We have G differentiated partially with respect to y, differentiated partially with respect to x, with respect to y, and then over here with respect to x, with respect to y, and then here in the corner we put 0. Or if you like, you can write it like this. So here we will have our f xx, f xy, f xy, f y y, and then we are going to border it on top. So most of the time we'll just use this one, but even if you use that one, you're going to get exactly the same thing. So when we border it, here we will have gx, gy, gx, gy, and then here on the major diagonal is where the 0 must be, okay? So it is the Hessian matrix, but you are bordering it. You can see here that is our border over there. And then with this one, this is our border, okay? And what you have here is the Hessian matrix. So you have the Hessian matrix, and then you are bordering it with this constraint function, and that is why it is called the bordered Hessian matrix. Now, how do we classify it? Now, the way to classify the classification very simple, is that if this determinant is negative, then you have a minimum. And then if the determinant is positive, then you have a maximum. Okay, so that's basically how we classify it. So you'll find this determinant, and then if it's positive, you have a maximum. If it's negative, then you have a minimum. All right, so let's look at an example of this. Given z is equal to 4x squared plus 3xy plus y squared, subject to this constraint that x plus y is equal to 56. The bordered Hessian can be used to check the second order conditions for the optimized function. And then we want to see, is z going to be maximized or minimized? Okay, so first thing we need to do is come up with our new Lagrange equation. And this one, just like we did, or I showed you previously, this is equal to this function here. So we have 4x squared plus 3xy plus 6y squared. And then we add lambda. And then what we do is this x and y, we take them over to this side. So what we end up with is 56. This is our k minus x minus y. Okay, so we take these to the side of our constant. So instead of k, our k here is equal to 56. So here we have 56 minus x minus y. All right. Then we proceed as we normally do. We want our bordered Hessian determinant. So to do that, we need our first order partial derivatives as well as our second order partial derivatives. So we look for zx. So differentiate this. Or maybe first, it might be easier if we multiply everything out. So we can do that. So 4x squared plus 3xy plus 6y squared plus 56 lambda minus x lambda minus y lambda. So lambda is a Greek letter. So x, this is lambda. It's a Greek letter. Okay. All right. So we find zx. The derivative is 8x. The derivative is 3y. The derivative is 0. The derivative is 0. The derivative is minus lambda. And the derivative is 0. Then we find zy. The derivative is 0. The derivative is 3x. Then the derivative is 12y. The derivative is 0. The derivative is 0. And here the derivative is minus lambda. Okay, if we were trying to work out the actual critical point, then we'd equate them to 0, solve them simultaneously, but we're not trying to do that. We just want to find out if the z is maximized or minimized. So we need to work out our second order partial derivatives, zxx. So here we have the derivative is 8, derivative is 0, derivative is 0. Then we look for zxy or zyx. We differentiate this one with respect to x, we would get 3. We differentiate this one with respect to y, we would also get 3. We know that they must be equal. And then we have zyy. So this is 0, and this gives us 12. Okay, now our g of x, our g function, this is the function x plus y is equal to 56. So we differentiate this one, we get g of x, this is 1, g of y, this is equal to 1, because this is what we are going to use to border our function. All right, now we look for the bordered. Remember to put the bar that is telling you that it is bordered. Okay, and here we're going to use this one where we have f, I'm saying f, but it's z in this case. It's zxx, zxy, zxy, zyy, and then we border it gx, gy, gx, gy, and here we have 0 over there. Okay, so zxx, this is 8. Here we have 3. Here we have 1. Here we have 3. We have 12. We have 1 with 1 with 1, and then we have 0. So basically what we need to do is work out the determinant of this matrix. This is a 3 by 3 matrix. We know how to work out its determinant. It's simple and straightforward. So we have this. If we use our cofactor method, you're free to use the method of diagonals, that's fine. So we'd say 8, it's positive because of the plus here. We multiply, I remove the row, remove the column. So we have 12 times 0 minus, remove the row, remove the column, 1 times 1. And then negative, because of this negative here, with negative 3, remove the row, remove the column, so 3 times 0 minus 1 times 1, and then we have plus 1. Remove the row, remove the column, so we have 3 times 1 minus 1 times 12, and when we work this out, we get negative 14. So here we just need to classify it based on our answer here. Negative 14 is less than 0. Then we can say that since our bordered determinant is less than 0, this means we have a minimum. Just write it better. It means we have a minimum. Okay, or Z is at a minimum. Right, so here's another example where we have a function here that is subject to the constraint x squared plus y squared is equal to 1. So first thing we would want to do again is find the function. So this function, we can call it capital F. This is going to be f of xy plus lambda multiplied by k minus g of xy. So this is the formula we know already. And what is this going to give us? A function f, this is xy. And then we add lambda. Our k is 1, so we say 1 minus x squared minus y squared. So and then if we multiply everything out, we have xy plus lambda minus lambda x squared minus lambda y squared. So this is our function over here. So notice we're not given any critical points, so we might want to work out. So we find fx. This is derivative, this one with respect to x is y. This is 0, then the 2 will come down, so we have minus 2 lambda x, and this derivative is 0. So fy, this is x, derivative is 0, derivative is 0, the 2 will come down, so I have minus 2 lambda y. And then we have f with respect to lambda. So this is 0, this is 1, this is minus x squared, and this is minus y squared. And we know that at our critical points, each of these must be equal to 0. Let me say that at the critical points, and this is equal to 0. Okay, so we are going to solve them simultaneously. So we say y minus 2 lambda x is equal to 0. So from here we can see that y is equal to 2 lambda x. From the second one, x minus 2 lambda y is equal to 0. So this means that x is equal to 2 lambda y. And 1 minus x squared minus y squared is equal to 0. This means that x squared plus y squared is equal to 1. Okay, so from each of these, you can square this, you get y squared, then you substitute it here. Same thing here, you can square this, substitute it in there, then we will have an equation with x, y, and lambda, but that is probably easier to solve than just all these three together. Okay, so if I do that, I have x squared here. This x squared is 2 lambda y. So basically what I'm doing is substituting. Okay, then I have plus 2 lambda x, this is squared, and this is equal to 1. So if I expand my brackets, I have 4 lambda squared y squared plus 4 lambda squared x squared. This is equal to 1. And I can see that 4 lambda squared is a common factor, so we take it out. So I have 4 lambda squared, and then I have y squared plus x squared. This is equal to 1. And this one over here, y squared plus x squared, is exactly equal to this. So this means that this is 4 lambda squared times 1 is equal to 1, because x squared plus y squared is the same as y squared plus x squared. So this is equal to 1. So what I actually have is 4 lambda squared is equal to 1. This lambda squared is equal to 1, 4, and this that lambda is equal to plus or minus a half. So we take the plus or minus square root on both sides. Okay. So you can also go ahead and solve for x and y, because we now know what lambda is. Go back here, we substitute. If, for example, so there'll be more than one critical point that is normal. So if we say lambda is equal to positive half, so if lambda is equal to positive half, this means x is equal to 2 times half times y. So this just means x is equal to y. Then I can substitute it over here. So x is equal to y, so this means the equation x squared plus y squared is equal to 1. Instead of y squared, I just have x squared because x is equal to y. So I have x squared plus y squared is equal to 1. I'm repeating it. So instead of y squared, I have another x squared is equal to 1. So we have 2x squared is equal to 1. So this means x squared is equal to half. And then this means x is equal to, and so minus the square root of half. So this is plus or minus the square root of 2 over 2. So one critical point would be, let's say, square root of 2 over 2, and this is x, but now x is equal to y, so we have square root of 2 over 2, and another one is negative square root of 2 over 2, and negative square root of 2 over 2, and this is when lambda is equal to a half. Okay. So we would find several critical points. So for you, try what happens or what are the values of x when lambda is equal to negative a half. Okay, so doing that, we now continue to use our bordered Hessian determinant. Okay, so now we want to come up with our bordered Hessian. So we have our, okay, like this. We know the formula, so we will have fxx, fxy, fyx, which is the same as fxy, fyy. Here we have gx, gy, gx, gy, and then over here we have 0. So this second order partial derivatives, we still need to work them out. So fxx, this is derivative of this one is 0. The derivative here is minus 2 lambda. Then fxy, this is just 1. Fyx is obviously also just equal to 1. And then fyy, this is equal to minus 2 lambda. Okay, then we need g partially differentiated with respect to x. We get 2x Okay, and then g partially differentiated with respect to y, we get 2y. All right, then we substitute them into our matrix. Fx is minus 2 lambda. Fxy, we have 1, and then gx is 2x. Then here we have 1 minus 2 lambda, and here we have 2y. Here we have 2x, we have 2y, and then 0 goes over here. This is a 3 by 3 determinant, which we know how to do either using cofactor method, or we can use the method of diagonals. So if we use the cofactor method, we have minus 2 lambda. Remove the row, remove the column. This will be 0 minus 2y times 2y, and then negative 1. Remove the row, remove the column. This is 0 minus 2x times 2y, and then we add 2x. Remove the row, remove the column. We have 1 times 2y, just 2y, and then minus, just make some space. So remove the row, remove the column. So we have this minus negative 2 lambda times 2x minus. Okay, so we have minus 2 lambda. This is negative 4y squared. Then we have minus, then negative 4xy. Then we have 2x, and this is 2y. Negative and negative will give us positive 4 lambda x. So I want to multiply out our brackets. Okay, what's happening? Just bear with me. Okay, want to simplify. Negative and negative will give us positive 8 lambda y squared. Negative and negative will give us positive 4 xy, and here we have 4 xy, and this is 8 lambda x squared. Okay, so we have 8 lambda y squared plus 8 xy plus 8 lambda x squared. All right, then we just need to substitute our values of x, y, and lambda. So this is x, this is y, and this is lambda. And it's freezing. So this is half, then we have the square root of 2 over 2. This is squared, and then this is 8. The square root of 2 over 2 times the square root of 2 over 2. And we have 8 times a half. And then we have the square root of 2 over 2 times the square root of 2 over 2. This is squared. Okay, this is not correct here. And write that correctly. So this one should not be there. And it should be squared here. Okay, so this you can obviously work out on your calculator, but it's not difficult to do even without a calculator. So 8 times half is 4, and when we square this, we have 2 over 4, which is a half. Okay, and then we have 8 here. This is 2 over 4, which is a half. And then 8 times a half is 4, and this is 2 over 4, which is a half. So this is 2 plus 4 plus 2, and this is equal to 8. So this is positive That means we have a maximum at the point square root of 2 over 2, square root of 2 over 2. You can say that. Okay, so you can see that there's 3 other critical points. So what you can do is find the other 2 critical, or 3, because we only worked out 2 of them. But the next one, the second one is not difficult to work out. So because lambda is still a half, but this time x is negative square root of 2 over 2, and x and y are equal, so that's easy to work out. Then the next one you try when lambda is equal to negative a half, then work out the critical points associated with that, and then you would test them in the same way. So that's basically it on the board in Hessian. You can see it's not very difficult to do. What you need to know is how to differentiate. And then the last thing is how to plus